Hello. Here we will look at what is called Pythagorean triple, and that is the triple of integers which solve the Pythagoras equation. So we'll be interested in finding x, y, and z integers which satisfy this relation. And this relation is what is called homogeneous. So if you have one solution, one triple of integers, you can scale it up or down with any coefficient. So down has to be a divisor of all of 3, and that still be a solution. So what you can do, you could look at groups or sequences of those which are scalings of each other, and in each such group you will have a unique representative where the triple is mutually coprime, so the greatest common divisor of the triple is 1. Such are called primitive, and that is a way of eliminating this freedom of scaling. So we'll be interested in finding them all some clever way. And there is such a way, and I will be using the trick which will reduce the number of variables in the Pythagoras equation from 3 to 2. Again, using the homogeneity of this, I can just take z and divide everything by z squared. So in this way, I will have just 2 unknowns left. Right hand side will become 1, and the first will be x over z, and v will be y over z. So these are really this is really the way of transforming the Pythagorean triple into a pair of, now u and v are ratios of integers, will have to be rational. A pair of rational numbers being coordinates of a point on the unit circle. So the real trick to label, to account for all Pythagorean triples, is to first switch to this 2-variable case and then use geometry. Here I will try to draw a unit circle, so imagine that it is really a circle of radius 1. So this point has x, rather u coordinate -1. And I will be interested in finding all rational points on this unit circle. And the trick is to label them by some other quantity. Well, instead of the pair of coordinates of two rational numbers, introduce just one, because after all we are looking at a curve, so we should have one parameter for this curve, but we have to choose this parameter carefully so that rationality of coordinates is preserved. So this is the trick, this is the choice. Let's just connect the special point on the circle, this point with the coordinate -1, 0. Let's connect it with our arbitrary rational point and then measure this elevation. Let's call it t. So the first easy statement: if this point has rational coordinates u and v, then this t has to be rational. So the first statement. And that is easy, because if u and v are both rational numbers, then this line must have rational coefficients, line equation, and hence the y or the v-intercept of this line will have to be rational. So that is clear from just basic geometric and algebraic facts. The converse is also true, but to prove the converse, we will have to find really the expressions for u and v in terms of this height t. So let's see how can we compute, knowing this this number, how can we compute the coordinates u and v. and what will be the expressions. And by the geometry, by our design, this is one of the two intersection points of this line with the unit circle. So let's write the line equation passing through these 2 points. One point is with coordinates -1, 0, and so the line equation will be proportional to u plus 1, because at u equal -1 the line function has to take 0 value. And then the proportionality coefficient can be determined by this data, by the fact that the value of the line function at 0 is t. So when we substitute 0 here, then this will become 1, and so the prefactor has to be t. So that is our line equation. That is the equation of the line passing through the 2 points. Now we have to solve it together with the circle equation, and that becomes that gives us a quadratic equation. All squared, right? And of course we can solve it and find 2 solutions, but we know that one of the solutions will be u equals -1. So we really want to eliminate it and really just look for the second solution for the u coordinate here. So the way to eliminate it is with the help of some trickery. Let's just, the way of eliminating this unwanted solution is just take u squared, put it on the other side, and then factorize. Now we have 1 plus u on both sides, which we can cancel assuming that u is not equal to -1. So just ignoring this obvious solution, this obvious intersection point. We will have linear equation after cancellation, which is with unique solution u, which will be that coordinate. So collecting the u coefficients, we will have t squared plus 1 u, and then t squared we can put on the other side, so it will be 1 minus t squared. So that gives us u 1 minus t squared over 1 plus t squared. All that's left is to find v from the line equation, for example, and that will be this, but then simplifying, putting it's all over common denominator, we will have 1 minus t squared and then plus 1 plus t squared. And the cancellation gives us 2, so the total is 2t over 1 plus t squared. And these are the coordinates of the point. So the u coordinate is 1 minus t squared over 1 plus t squared. The coordinate is 2t 1 plus t squared. That is labeling in terms of this parameter t of all the points on the circle. So really we don't care here in this computation if t is rational or not. It's just the one parameter parameterization of the circle, and the parameter works well apart from the point where t becomes infinite. So this point corresponds to the line which really goes up and up and up and then becomes vertical, or goes down, down, down and becomes vertical. So that is the point which is supposed to be assigned to the t value plus or minus infinity. And the rest of t values will give us points on the circle. So for example, if we look at t between 0 and 1, we will have the first quadrant covered, and for this quadrant we'll have to look at values of t larger than 1, and similarly for the negative half. So this is a parameterization which now will allow us to conclude the opposite implication. If t is rational, then both functions will give us well-defined rational numbers, and so we will have a rational point on the circle. So that is now both ways statement the pair of coordinates is rational if and only if this line drawn through that point and this point will have a rational intercept and vice versa. Now we can use this to label all rational solutions, of course, of the circle equation, but then go back and find presentations for all possible x, y, and z. And we could now write our parameter t, which is a rational number, as a ratio of two integers. Could even assume that they are coprime. And then compute u and v in terms of these integers. So u is 1 minus the square over 1 plus the square. And so making common denominator and squared, upstairs and downstairs we will have n squared minus m squared over n squared plus m squared. So v is 2 m over n over all over 1 plus m squared over n squared. And again, doing the necessary algebra, we will have this answer. And now we can clear the denominator. So we have rational u, rational v. We can clear the common denominator n squared plus m squared and have a solution in three variable case, the Pythagorean triple. So we'll have n squared minus m squared for x, for y 2mn, and for z n squared plus m squared. And the claim now is that in any class up to rescaling, we will have a solution found this way. So we really find all solutions if we allow to compute using this procedure and then rescale. So that is, up to scaling is everything. Or we could say it this way: we can take any mn, compute this triple, and then if necessary cancel by the greatest common divisor of the three. So if there is anything dividing them three, we can cancel it out. And that way we will account for all primitive Pythagorean triples. So let's experiment. Let's just look for small values of m and n and recompute compute x, y, and z coordinates. And yeah, if we want just to see things in the first quadrant or to see positive x, y, z, we can assume that m is not larger than n, or actually smaller than. So 1 and 2 would be the first choice. X, y, z will be 2 squared without 1 squared, 3. Here we'll have 2, 2, or 2, 1, 2, just 4, and this is the sum of squares of 1 and 2, and that becomes 5, and that's the well-known Pythagorean triple, the smallest such. So if we increase n by 1 now and recompute x, y, and z, so this time we'll have 9 squared without 1 squared, which is 8. So here we'll have a product of 2, and 3 and 1, that is 6, and here we'll have the sum of 9 and 1, and that is 10. And that is not a primitive triple, that is reducible down to 4, 3, 5. And we recover almost the same as this triple up to swap of x and y, which is of course a freedom for Pythagorean triples we can always employ. Let me compute one more. So pair 2 and 3. Now this is the difference of 3 squared and 2 squared, so that will be 5. Here I have the product of 2 and 2 and 3, so that will be 12. Here I have the sum of 2 squared and 3 squared, and that is 13. And that is a primitive Pythagorean triple, so that is not reduced to anything. And of course, knowing up to scaling the shapes of the coordinates will allow us to do some more delicate things, like imagine that we have the right hand side coordinate fixed. So imagine that we're looking at the prime number 17 and want to see all solutions with this z coordinate, and the question is, are there non-trivial solutions, not those which are 0 and then 17 in the second coordinate? And yes, the question is that there are, because 17, we can take it as the z coordinate, is possible to write as a sum of squares. And that is crucial now, because up to scaling we have to be able to write our last coordinate as a sum of squares, and that only possible for prime numbers which are of the form 1 plus a multiple of 4. So 17 is one of those. 17 can be written as 1 plus 4 squared, and so we can think of m and n as 1 and 4 and recompute the other two coordinates and have a Pythagorean triple. So the product of 1 and 4 and 2 is going to be 8, that is our y coordinate, and the difference of squares of 4 and 1 will be 15. And again, it's a primitive Pythagorean triple because, of course, the last coordinate is a prime number. And in the same way, we can be sure that if we choose it to be 11, the z-coordinate, then there will be no solutions but trivial. So these will be the only solution up to swap of x and y and maybe changing signs, because 11 is not possible to write as a sum of squares. So that is it. See you later.